All right, next I'd like to talk about what's usually referred to as the derivative theorem for Fourier transforms. And I'd like to do it for distributions and Fourier transforms. But first of all, let's just state it. So derivative theorem for Fourier transforms. And there are two parts to it. One part is that it says if I take the Fourier transform of the derivative of little f, then that's the same as 2 pi I s times the Fourier transform of f. Okay? So in the usual case, we're thinking of the input to the Fourier transform is a function of t, and then the output, of course, the Fourier transform is a function of s, and then this is a function of s here as well. So that's one statement. And then going in the other direction, if I take the Fourier transform of f, but I take the derivative of that, right? So the prime here, of course, is derivative with respect to t. The prime here is now derivative with respect to s, because we've got a function of s being the Fourier transform, or whatever, however you wanted to make those variables. S and t are a bit arbitrary as well. But in any case, if I take the Fourier transform of this, and then I take the derivative with respect to s, it's the same as taking the Fourier transform of the function minus 2 pi I t f. Okay, so operating in the time domain, right, as a constant times t times f, right, taking the Fourier transform of that is actually the same thing as taking the Fourier transform and then the derivative, or multiplying with a constant times the Fourier transform, constant times s, right, is the same thing as taking the derivative in the time domain over here. All right, these I will leave as a homework exercise. So expect to see those coming up on another homework. Of course, to prove these, we're in the infinite domain, right? We're in, this is in, we're talking about our signal processing world 4, meaning infinite domains. Continuous and infinite on both of the domains, right? So that's our signal processing world number 4. And then here, of course, you would just be proving these with those definitions of the Fourier transform involving that integral from minus infinity to infinity, or for the inverse Fourier transform similar. All right. So in these two cases, you can show that pretty easily. We also get the same derivative theorem then works for distributions. And so let's just take a look at that. So what happens when I take the Fourier transform of a distribution, and then I take its derivative, and I apply that to phi? Well, as we know, first of all, we can unwrap this over here on the left side, right? We can say the first thing I can take here is the derivative and push that over onto phi and also put a minus. Remember, that's how we define the derivative of a distribution. So I get Fourier transform of t and then phi prime. And then I get, from this, I can also then say the definition of Fourier transform is push that over onto the Schwartz function. So I get minus, and then t, and then here I get the Fourier transform of phi prime. Well, continuing from the above properties then, this is equal to minus, and then t, and then over there on the right, the Fourier transform of phi prime, right, by the first property up there, gives me 2 pi I s, and then Fourier transform of phi. And of course, this is now function times another Schwartz function here, but I can just take that function and multiply it times my original, right? So I get minus, and then I can also multiply in the minus operator as well. So I get minus 2 pi I s t, and then acting on the Fourier transform of phi. But again, doing the Fourier transform here is the same as doing it over there. So we kind of have unwrapped and then rewrapped on the left-hand side, and we get all the way down to then Fourier transform of minus 2 pi I s t, and then acting on B, right? So I guess I proved them in the opposite order. So in any case, this implies the following then, that the Fourier transform of t prime equals the Fourier transform of minus 2 pi I s t. Okay, so that's one of our two statements. In fact, it's the second one here, right? But now in simply replacing a function by a distribution. Works in general now for distributions. All right. Let's also do the other one. So we can also check then that Fourier transform of t prime. We're now taking the derivative first in this case, right? Acting on our Schwartz function phi. So this is the same as t prime, and then Fourier transform of phi. And so now I expand out the derivative, right, by going minus, and then t, and then here I take Fourier transform of phi, the derivative of that second part, and now that's minus, and then t, and now this part I can use, I can apply that second property there, right? So that's going to be Fourier transform of minus 2 pi I t phi. And so that's minus Fourier transform of t, moving the Fourier transform back over now. That's minus Fourier transform of t, and then minus 2 pi I t phi. Now I've got product of this function times the phi function. I can do product of function times a distribution over there. So that's going to be minus, and then I got minus 2 pi I t Fourier transform of t phi. And then finally, that is going to be so in this case here, this we should just change to be an s, right? Because I've got this, we're thinking of as being a function of s, so I've got minus 2 pi I s t, Fourier transform of t phi, and then of course I've got the double negative, so this is just 2 pi I s, and then Fourier transform of t phi. Okay? And so this tells me the other property then just comes down as Fourier transform of t Fourier transform of t prime is just equal to 2 pi I s, and then Fourier transform of t. And that's our second property, which was the one that was listed first up here.